Good morning, lads and ladies. Welcome back to College Algebra. I'm excited today to share with you a little bit more about logarithms. Oh, my shirt has a hole. I'm excited today to share a little bit more with you about logarithms. Last time we got a basic feel for what logarithms are about, what they are, the definition, how to compute, particular logs where we can by hand, and how to use the calculator to compute specific values of logarithms, either using the change of base formula or using the appropriate function in the TI-84 to do an arbitrary base logarithm. Today I want to do just one or two more things kind of like that before we stretch forwards into the next section, which is like algebraic properties of logarithms, totally its own thing, but also connected to what we've been doing. So let me go ahead and flip on the screen share. Connect this thing. All right. And let me see, I'm curious, did I upload that for you guys? I have a packet for this that I think y'all might like. Either put it in the modules or in the files. Oh, files. No. All right. We'll do that later then. Okay. So this is MAC1105, College Algebra. This is section 007. This is a lecture, and today is the 8th of April, 2021. Today, talk more about logarithms. I'll look at a few more problems from that earlier homework set, the first homework set on logs, which was, where'd you go, buddy? Homework 19. But then we're going to talk about log properties. Which is homework 20. And those are the two homeworks that are due, remember, at the start of class next week. So log properties, these are those things I was hinting at the end of our lecture on Tuesday. You might be tempted to like try to cancel or manipulate or expand or distribute, do things with logarithms. But trust me when I say most of those things are not kosher. I will show you the things which are kosher today. I just said something in the chat. Yeah, we can look at an example or two from homework 19. I would be happy to do that. Let's go ahead and dive in, why don't we? Sure. So I do have this open. Let me see what exercise 21 is. I had a few particular ones in mind. Is it a continuous rate of 9.4% a year? Yeah, sure. Starts to see grams. All right. Before we get to that, so somebody in chat requested number 21. We will do that, but I'd like to come back just a little bit and do one or two slightly more basic problems, just to make sure we're on the same page. I think maybe I'll start with something like number 16. 16, 17 first, something like that. Maybe I should remind you first, we have these, so I give you two definitions of the logarithm, right? They're equivalent, but sometimes it's easier to think of this one way than another. So the first definition was all in words. We said that the base A logarithm of, or just the base A logarithm function is the inverse of the base A exponential function. Now this is all well and good So, you know, if f of x is the function a to the x, then f inverse of x is the log base a of x. This is useful when you're thinking about graphs, when you're thinking about domains and range, when you're thinking about points that should be on the graph of the logarithm function, all of that stuff, right? Because we have this cool relationship between the original function and its inverse. We know that, like, you know, the ordered pairs flip around. We know that domains and ranges switch. Excuse me, all that good stuff. The second definition we had, I'm going to give you another definition after this today. The second one that we had, our first alternate definition, was, you know, if a and y are positive numbers, then a to the x equals y is equivalent to saying that x is equal to the base a logarithm of y. If you think about it, these really do say the same thing. And there is a final characterization. So this is what we found is mostly useful for solving problems, right? This is the one I put in the blue box in our lecture on Tuesday. If you've come to office hours to solve problems with me since then, this is what we use. This is what we use for all of our work in class on Tuesday as well. Another sort of recharacterization, another way of saying this, and I wouldn't even say it's a different thing than this first one. Again, these are all equivalent. But what does it mean for two functions to be inverses? That means that one undoes the other. If you plug one into the other, then they kind of cancel each other, right? In the same way that, like, x squared and the square root of x, when you plug one into the other, sort of cancel each other. So again, what we could say here is that a raised to the power of the base a logarithm of x should be x, and the base a logarithm of a to the x should be x. That's the game. So this is your final characterization of the log. And this is really just the algebra version of the very first one. All right, remember, what does it mean for two functions to be inverses? It means when you compose them, when you plug one into the other, you just get x. So here I'm saying these are inverses. Here I'm saying when I compose them, I just get x. Like when I take a to some stuff, that's this function. But for x, I plug in log base a of x. So this would be f of f inverse of x. I just get x. And this one says the same thing, but in the other way. It says that f inverse of f of x is just x. So you may recognize these as being the algebraic characterization of an inverse function. In practice, it's these two different things, mostly this for computing logarithms and this for solving equations that we use. So I wanted to make sure you get this one in your notes. This is kind of new, and you might not have deduced it on your own from this, which is fine. I get that. So let's go ahead and solve a handful of problems. I think we said we want to do like 16, 17, and then somebody wanted to see related problems. So we'll do both 16 and 17. 16 says solve the equation 4 times 10 to the 2x equals 43. I'm going to change the numbers just a little bit. And let's ask for our answer in the same precision they want. So they say, correct answer, type an integer or fraction. Oh, no, here we go. Integer or decimal rounded to the nearest 100. So round to the nearest 100. We looked at some things like this the other day. And remember, the goal is to get this expression into the form a to the x equals y, because then I can rewrite it as a logarithm statement. So here's what I would do. I would say 3 times 10 to the 5x equals 27 is equivalent to, I've got my 10 to the 5x, my x is a part of this piece. So I should try to get this piece alone, which means I should first divide both sides by 3. If I divide both sides by 3, I'll get 10 to the 5x equals 27 divided by 3 is 9. Oh, 9. There's a few ways to proceed from here. Remember from our work on the previous section, the previous homework, I can rewrite 10 to the 5x as 10 to the 5 all to the x. So that gives me this. 10 to the 5, I can go ahead and write as a number here if I want. 10 to the 5 is 100,000. So this is 100,000 to the x equals 9. Should take a second, make sure you're comfy with this. Any questions about how we get to this line? Once we're here, we're pretty much done. Okay, so this is now of the form a to the x equals y, right? This is in that form that I can rewrite now by the definition of logarithm. This is equivalent to saying x is equal to the log base 100,000 of 9. Which I could write using the change of base formula as the ln of 9 over the ln of 100,000. So let's pull up our calculator. And we'll see how to crunch this both ways, whether you have the 84 with the log base function or you don't. Honestly, I think scrolling through and opening that log base function is more work than it's worth. I would just go, okay, ln of 9 divided by ln of 100,000. Measure it. However, if you really like that log base function, you can hit math, scroll all the way down to log base here, and say log base 100,000 of 9. And you get the same answer. So if you're asked for the exact answer, you'd say it's either the log base 100,000 of 9 or ln 9 over ln of 100,000. But here we were asked for the approximate answer, round to the nearest 100, rounded to 100th is 2 decimal places. And there we would say x is approximately equal to 0.19. All right, so this is your exact answer. You could give it in either of these forms. Or like this question asked you for an approximate answer rounded to 2 decimals. What I'm going to show you today using properties of logarithms, slightly faster ways to solve equations like these, and some tools that will allow us to solve more complicated equations than these. So I want to make sure before we move on, are we all 100% comfortable with how we solve this equation? Are there any questions at all about what we did to get from this equation to either forms of this answer? Okay, all right, then we'll charge forwards then. Oh. This is something that you're showing in chat. Sure. All right. I'd like to look at one more of these. I was leaning towards number 17 here. So let's get the both exact and approximate solution, number 17. And again, I'll change the numbers just a little bit. And say state the exact answer. And the decimal. All right. So we want to solve the equation e to the x minus 7 is equal to 14. Equations like this are called exponential equations because they involve exponential functions. That last one was also an exponential equation. And your homework next week is going to be full of exponential and logarithm equations. So I would like you to tell me what would be a good first step here. How do I get started? Yeah, excellent, Kendra. So we want to get the term that has the x in it alone. To do that, we need to get rid of the 7. So we're going to add 7 to both sides. So when I add 7 over here, the 7 will go away. When I add 7 on the right-hand side, 14 plus 7 is 21. All right, what do I do now? Very good. So we can rewrite this using natural logs. This is the same as saying x is equal to the ln of 21. There's a handful of ways to think about it. You could say I'm going to take the natural log of both sides, and over here the natural log of e to the x will just be x. Or you can use the definition and just say this is a consequence of the definition. So the ln of e to the x, the intermediate step there would look like this, the ln of 21. And then the ln of e to the x is just x. And so what Brooke's saying in chat there is kind of the approach that the way we'll be thinking about these things moving forward is using properties of logarithms. This is precisely the alternate definition to the second part of this, where you take the ln of e to the x and just simplify it to x. The log base a of a to the x simplifies to x. So you can think of it as coming from the second definition like this, or from the third definition like this. Either way, we get the natural log of 21. And the natural log of 21 3.0445, blah, blah, blah. So we wanted to round to 3 decimal places, so that'd be 3.045. All right. So it seems like you guys are pretty comfy with these basics. Let's take a look at the problem Sophia wanted to see. Or no, homework 19, what was it? Number 21, right? Yeah, so you've got a substance starting with C grams and decaying at a continuous rate of 9.4% per year. So this is one of these things we're going to have to kind of combine the very last model that we talked about last week. And then presumably do some work with logarithms to work out the remainder. So let me just get this copied down. We've got a substance currently C grams. Continuous rate of 9.5% per year. Create a model after X years. Per year. Create a model for the amount A left after X years. Okay. So remember that at the end of class last Thursday, we talked about this continuously compounded interest function, right? We discovered that number E, and then we said, okay, this is what's called continuously compounded interest because we're compounding at every moment in time. We're setting n to infinity. We also said that if you see something saying you're growing or decaying at a continuous rate, we use that same function. The reason for that is from calculus. It's that at any moment in time, the rate of change, the instantaneous rate of change for that sort of function would be this number, R. So the continuous growth or decay function, I hate the use of this word, continuous growth decay function. This is already as a of x here because that's the notation they've asked us to use, is the original amount times e raised to the rx. So this is the model that we need to begin with. So we had a different thing for the regular growth and decay rate, but this is like a continuous growth decay rate. Again, I'm as frustrated by the language as you are here, but it's because if you want to know, if you take the derivative of this, if you look for the instantaneous rate of change, like how fast is this function growing at any particular moment in time, it's proportional to this number r. That's why this number e is so special, and that's why we call the base e exponential the natural exponential, because it is always proportional to its own rate of change. But the upshot is you just need to know to use this formula when you see this word's continuous rate. The other thing you need to be careful about here is that we're decaying. So this rate should really be negative when we employ it in this formula, right? We're not growing, we're decaying. So just like with the other growth and decay models, a negative rate corresponds to decay. Our function here, they haven't told us the original amount. They've just said we start with c grams and that we're decaying at the continuous rate of 9.5%. So for us, since we're decaying at 9.5% per year, R is negative 9.5%, which remember we need to rewrite this as a decimal. That's negative 0.095. So our model A is C. We don't know what C is. They told us it just starts with C grams, so we just leave it as C, times e to the negative 0.095 x. That's how much of this shit will be left after x years. Remember this. The decay here is what gives us the negative here. All right, so you see continuous rate or continuous compounding, you know you're going to use the natural exponential. You know you're going to use the e to the stuff formula, the formula with the e in it. And then if it's growth, r is positive. If it's decay, r is negative. Here, since we're decaying 9.5% per year, r would be negative 9.5%, which as a decimal is negative 0.095. So this is our function. This is our model. Now that we have our model, we can do whatever the hell they want with it. How long will it take for the substance to decay to 30% of the current amount? And after 16 years, there was this amount. All right, we'll figure that out in a second. So how long to get to 30% of the original amount? That's our first problem. I'll write the problems down here. How long? I said to get to 30% or to lose 30%? To decrease to 30% of its original amount. To decrease to 30% of the original amount. And part B, if after 16 years there were 950 grams, how much was it? Was there original? All right. So for part A, 30% of the original amount well, the original amount is C, right? I said, you know, originally there was C grams. Right? Substance currently consists of C grams. So 30% of that is 30% of C, or 0.30 times C. So if I want to know how long will it take for this substance to decay to 30% of the original amount, I need to know when is this function equal to this. So I need to solve the equation C times e to the negative 0.095x equals 0.30 times C. But we can begin by dividing both sides by C's. The C's cancel. So if you divide both sides by C, you get e to the negative 0.095x equals 0.30. The most natural way to proceed from here is to start using that third characterization of the logarithm, right? We could write this as e to the negative 0.095 all to the x, and then try to rewrite that using the base logarithm e to the negative 0.095. But that's sloppy. So the nice thing to do here, and this is sort of the new important verb, you heard Brooke use it in chat, we're going to take ln of both sides. When you're solving exponential equations, especially exponential equations that involve the number e, once you get your exponential term isolated, you want to take the natural log of both sides. This is the kind of big new thing. So if I take the natural log of both sides, I'll get the natural log of e to the negative 0.095x equals the natural log of 0.30. The neat thing about this is that the natural log of e to some shit is always just that shit. So the ln of e to some shit will always just be that shit. That's again what this says, right? Particularly this one, the bottom one. Here, if you use the base e, a log sub e is just ln. So the natural log of e to the x would always just be x. And I don't care what x is. The natural log of e to some stuff is always just that stuff. Or the base a log of a to some stuff is always just that stuff. So this becomes negative 0.095x equals the natural log of 0.30. And I can then divide both sides by a negative 0.095. So I get x equals the ln of 0.30 divided by negative 0.095. And that would be my exact answer. But they didn't want an exact answer. They wanted an approximation. So if I want to give a decimal approximation to this answer, I would say, okay, I'm going to take the ln of 0.30, close that parentheses, then divide this whole mess by negative 0.095. And I get 12.673. So wherever they wanted us to round, we could round. That's our answer. Little over 12.5 years. Questions on this process? This step is kind of a big deal, right? That you can take the log of both sides in an equation. You can go from an equation like this to an equation like this by taking the log of both sides. And this fact that the ln of e to some shit is always just that shit, it's a nice fact. The second part said if after 16 years, there is how much stuff? 950 grams. Find the original amount, find C. So I need to take my model and interpret that statement here in the context of my model. So after x years, I know a of x is C times e to the negative 0.095x. The statement after 16 years, there's 950 grams, means a of 16 is equal to 950. So what is a of 16? Well, a of 16 is C times e to the negative 0.095 times 16. And we said, okay, well, after 16 years, it's 950 grams. So that means this has to be 950. And now this is an expression we can solve for C. I want to get C alone, so I'm going to divide both sides by this quantity. That means C would be equal to 950 divided by e to the negative 0.095 times 16. And we can calculate this. So I take my 950. I divide it by E. So to get E, hit second, and then my eyes are so bad. Is it this? E, yeah. Raised to the power of, parentheses, negative 0.095 times 16. Close that paren, get down out of the power. Make sure everything looks good. It does. So we hit enter. 4,343.61, blah, 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 blah. Again, round wherever they tell you around. So the idea is by telling us how much there was left after 16 years, they let us set up an equation that we can solve for the constant C. So right away, they didn't tell us what C was, but they told us enough to get this function. And then in part B, they told us that A of 16 is 950, that after 16 years, there's 950 grams. So if I take this information and I plug it into this function, I get an equation that I can solve for C. This is what I get when I plug 16 into this function. And I know that after 16 years, there should be 950 grams. So I set that thing equal to 950. And then I just solve for C by dividing over by this chunk here. All right, we do need to talk about the new material. So this has been a fun run. But we do have new stuff to talk about today, namely properties of logarithms. each of the logarithm properties comes from a property for exponents. So of course you have those, you have this, right? This most people would not consider to be a property of logarithms. It's like a definition. But we absolutely use the shit out of this. So here's the log property. And over here, I'll put the corresponding exponent property. You know that if you take two numbers that are raised to powers, like bases, like a to the x times a to the y, then you can add the powers. This is the same as a to the x plus y. The corresponding rule for logarithms is that the base a log of a product of two things, x times y, is equal to the base a log of the first thing plus the base a log of the second thing. I'll let you think about how these are kind of similar. They each sort of take addition or multiplication into the other. The way I think of this, I say addition inside the log, or sorry, multiplication inside the log is addition outside the log. All right, so if you've got two things inside the log being multiplied, and that's the only thing going on, then you can rewrite that as the log of the first thing plus the log of the second thing. So multiplication inside becomes addition outside. This one we've talked about. If you have a to the x times y, that's the same as a to the x all raised to the power of y. The corresponding log rule is that if you have the base a log of something like x to the y, so inside here this is a power, that's the same as having y times the base a log of x. So in other words, powers inside can come down front as multiples. The last one of these has to do with division. So if you have something like a to the x divided by a to the y, like bases being divided, that's the same as a to the x minus y. And in terms of logarithms, we say that the base a log of x over y is the same as the base a log of x minus the base a log of y. So these are the three main rules for logarithms. And these are the only things you can do. Anything else, even if it looks like it should be okay, really isn't. Really is not. These are the only like algebra manipulations you can do with logarithms besides the straight up definition. So if you want to put it all in one place, I would say these together with the following facts. A raised to the base a log of x. This always simplifies to x. And the log base a
of a to the x always simplifies to x are the only allowed algebra maneuvers with logs. All right, this is it. This is what you're allowed to do with logs. If you do anything else, you're breaking the rules and shit's going to go haywire. All right. So let me look at a few problems from your second piece of homework this week. Properties of logs. Yeah, okay, so this is fine. Here they're just like writing down these properties of logs. They're not using parentheses as much as they should here, right? Like the M here and the N here should be in parens, but you recognize that these are the same sort of things that we've got there. So they ask us to compare the log 2, log 6, and log 12. And they're just asking us to do this with a calculator. Let me state this slightly differently. What is the relationship between ln of 3, ln of 5, ln of 15? Just for gets and jiggles, let's get out the calculator. The ln of 15 is like 2.7. The ln of 3, just 3, John, not 33. The ln of 3 is like 1.09. And the ln of 5 is like 1.6. So what's the relationship between these three numbers? ln of 15, which is, approximately 2.7, ln of 5, which is approximately 1.1, I'm sorry, 1.6, and the ln of 3, which is approximately 1.1. What if I just gave you these instead of calling them these? What if I just gave you these and asked, what's the relationship between them? Show me we're still awake. If I just gave you these blue numbers and I asked you, what is the relationship between these blue numbers? You would say, certainly that's true. But let's back up. Instead of giving a statement about logarithms, just give me a statement about these blue numbers. Forget that they have anything to do with logs. What's the relationship between 1.1, 1.6, and 2.7? Don't think too hard about this. My son's not even born yet. He could probably do it. I know you guys know this. You're just overthinking it, I promise you. Fuck yes, you add them up and you get the other one, right? This plus this is this. All right, this is something you guys all know. So what does that mean? So this plus this equals this. Well, that means that ln3 plus ln5 has to be ln15, right? Because these are those. Isn't that cool? I.e. ln3 plus ln5 equals ln of 15. Why does this work? Because by that, where was it? Because by this first property, the ln of a product of two numbers is the sum of the ln of those numbers. Why? Because 15 is 3 times 5. So ln of 15 is equal to the ln of 3 times 5 is equal to ln of 3 plus ln of 5 by property 1. You see what I mean when I say multiplication inside turns into addition outside? The ln of 3 times 5 turns into the ln of 3 plus the ln of 5. Multiplication inside turns into addition outside. All right, you have a few problems like this where they ask you, just what's the relationship between these things? And they're meant to help you sort of get comfy discovering how those properties apply. So like log 2 plus log 6, log 12, what's the relationship? Well, log 2 plus log 6 equals log 12. Why? Because this property. And we can play around with some other ones. But I'd like to look at something like this next. And again, they're really abusing things by not using parentheses here. Really should have the whole inside of the log in parentheses. But you can kind of tell the ln is written in bold. So you know that this stuff is all inside the log. It's just a little frustrating. So let's do some expanding problems. All right, so I'm going to give us two things here to expand. I want to expand the ln of 4x to the 10 and the base 3 logarithm of 5x cubed over z squared as much as we possibly can. What do I mean by expand? I mean use those properties to pull apart, to stretch out. All right. What do you see when you look at the ln of 4x to the 10? What sort of property could we apply here? Do we you see any multiplication inside that could be turned into addition outside? All right, this is the ln of 4 times x to the 10. So my first step expanding this would be to write it as the ln of 4 plus the ln of x to the 10. This is by property 1. From here, I can use property 2. Property 2 says if I have a log of a power, I can bring that power down in front of the logarithm. So the ln of 4, I'll leave him alone. But the ln of x to the 10 can be rewritten as 10 times the ln of x. This is by property 2. Yeah, very good. Thank you, Brooke. Technically, there's a little bit more that I could do here. 4 is 2 squared, or 2 times 2. So I could split that up a little bit further, but I'll leave it alone. It's just the log of a number. So if you gave me this on a test, good. All right, let's look at the other fellow. I have the base 3 log of 5x cubed over z squared. And I want to know, how can I start pulling this apart using those log properties? Remember, multiplication inside becomes addition outside. Powers inside become multiples outside. And division inside becomes subtraction outside. That was the third property. So I would get started here by saying this is the ln of the top minus the ln of the bottom. I'll say this, listen carefully. People get into trouble on these problems by trying to do too much at once. The way to get through these without making errors, losing points on the test, getting frustrated on the homework, don't do too much at once. One thing at a time, one property at a time. The first thing I see when I look at this is the inside is a big fraction. So I use property 3. I'll have the log with the same base 3 of the top, 5x cubed, minus the log with the same base, log base 3 of the bottom, z squared. This is by property 3. Division inside, subtraction outside. Here I could use property 2 to bring this power down in front. Here I can use property 1 to turn this multiplication, right, the product here, 5 times x cubed, into addition outside. And again, the trick is to do one thing at a time. So I'm going to just take care of this piece first. This is the log base 3 of 5 plus the log base 3 of x cubed. And I'll leave this guy alone, minus log base 3 of z squared. And the property I'm using here is property 1, just to go from this to this. on your work, you don't have to list the properties. I'm just doing this so you guys with your notes, you can go back and look in case you're having a hard time seeing or you want to review. All right, now what else could I do? Here I have a log of a power, and here I have a log of a power. So I can use that property too to bring both of those powers down. That'll give me this first piece, which isn't going to change, the base 3 log of 5, plus this power can come down. You have to just have a single thing raised to that power in order to apply this rule. Like I couldn't bring the 3 down at this stage. I could not bring this 3 down front here because the 5 isn't being raised to the 3, the z squared isn't being raised to the 3, only the x is. So you have to have something that looks just exactly like the property. You have to have just a log of a single thing raised to a power to do this. But at this stage we can. So that's 3 times the base 3 log of x. This power comes down. And then the same thing over here. I've got this minus still, but then this 2 is going to come down. 2 times the log base 3 of z. And here I'm using property 2. This might seem like kind of silly. You might be like, why do we even bother doing this? Because it's very useful for equation solving. It's also useful in calculus. When you're trying to do calculus operations on big complicated fractions, you split them up like this first, and it makes life easier. But for us, down the road, it's going to be very useful for equation solving. All right, any questions on how we got either of these? How we got this guy simplified to this, or expanded to this, I should say, or how we got this guy expanded to this. This would be our final answer. Okay. Not a whole lot left to say here, except that we can combine things as well. All right. I'll do one more example where instead of expanding, we're going to combine. Again, this page is kind of like your key or your Bible or whatever you want to call it. It's the thing that tells you precisely what's allowed. It's the constitution of logarithms. If it's not on this list, you can't do it. And there are a lot of ways to misinterpret these things. So please make sure when you're using a property of logarithms, when you're trying to change a logarithm statement into something else, make sure it looks exactly like this. One more. Two kids a little short. That's all right. Okay, so I want to combine these expressions into a single logarithm, and I'll give 2 to play with. How about 2 times the ln of x plus 3 times the ln of 2, let's say, minus 1/3 times the ln of y. about 5 times the log of 2 plus 1/2 times the log of x plus 1 minus 3 times the log of c, something like this. All right. So we want to combine these into a single log, right? I want to take this expression and rewrite it as the ln of one thing, just one ln. First thing I see is here I've got 2 times the ln of x, 3 times the ln of 2, and 1/3 times the ln of y. Each of these has a little constant or a number out in front of the log. So running those properties backwards, I can pull this 2 inside. I can pull this 3 inside, and I can pull this 1/3 inside as a power. All right, that's that property 3. It says powers inside the log are the same as multiples outside the log. So this is the same as the ln of x squared plus this is the same as the ln of 2 cubed minus this is the same as the ln of y to the 1/3 power. Does everybody see what's going on there? What we're using here is property 3. And then, just focusing sort of one thing at a time, I can use property 2 to take these 2 logs and combine them. Here I have 2 logs with addition on the outside, so I can combine those into a single log with the objects multiplied. So this is x squared times 2 to the 3. Those 2 logs combine into that. And then I still have over here minus ln of y to the 1/3. So I'm using here property 1. Oh, this power property was property 2, right? Not property 3. Sorry, numbering them wrong. Yeah, property 2. And then finally, I can use property 3 to rewrite this as the log of x squared times 2 to the 3rd divided by y to the 1/3. Yes, Kendra, there's no restriction on order. You can apply the properties in whatever order you need. You just need to make sure you're following the order of operations, right? Your regular algebraic order of operations. So for example, I couldn't, if I wanted to pull this back apart, if I wanted to take this ln of x squared times 2 cubed and pull it back apart, I couldn't pull this power, this 2, down in front because the 2 here is not being raised to the power of 2, it's being raised to the power of 3. Could the first log be ln of 2 times x to the 5? No, because these are not the same base, right? This is x to the 2 times 2 to the 3. 2 to the 3 is 8. So this is really 8x squared inside the logarithm here. So we can't combine the 2 terms inside the log like that because they're not like terms. If this was x to the 2 times x to the 3, I could write that as x to the 5. But x squared times 2 to the 3 is not the same as 2x to the 5. So I see what you're thinking, right? We want to add the powers, but that only works if the bases are the same. Here, this is a base x, and this is a base 2. So I can't add these powers because these are not like terms. My last step here would be to use property 3 to write this as a single log now. The inside would be x squared times 2 to the 3 over y to the 1/3. And just a quick comment, we can clean this up more. 2 to the 3 is 8. So this is the ln of 8x squared. And then y to the 1/3, that's the cube root of y. I think this is about as nice as we can hope to get this. And this last move to go from here to here is property 3. Are we comfy with why I can't combine these guys? That doesn't necessarily have anything to do with logarithms. It's just that those are not like terms. They don't have the same base. All right, let's try part B. Just like in the last one, each of these constants out front can come inside as a power. So I'll have the log of 2 to the 5 plus the log of, and be careful with this, parentheses x plus 1 all to the 1/2 like this. This 1/2 power is coming inside. That means this whole thing inside gets raised to that power. And then minus the log of z cubed. Before I go ahead and do any other properties, let me just clean this up. 2 to the 5 is 32. X plus 1 all to the 1/2, it's the square root of x plus 1. And z cubed is z cubed. I think sort of simplifying these pieces can make it easier to see what to do, right? If we wrote this as an 8, then you see x squared times 8. I don't think anybody would be tempted to combine those. So if it makes things clearer to you to simplify in between each of the properties, each of the log steps, don't hesitate to do that. Now these first two logarithms are being added. So this is the log of 32 times the square root of x plus 1 minus the log of z cubed. And then my last step would be to use property 3 to say these two logs being subtracted are a single log with the insides divided. Now I want to make a quick comment here, and this will be the last thing I say. Probably the most common mistake I see would be writing this last step as log 32 times the square root of x plus 1 divided by log of z cubed. But these are not the same thing. This is your correct answer right here. And it's very, very different from this. So this rule with subtraction outside to division inside, you should never have like log over log. The only time you should divide two logarithms like this is when you're using the change of base formula. If you're combining or expanding things and you find yourself writing something like this, log of one thing divided by log of another thing, you made a mistake. It's a super common mistake, but it's not okay. It's not at all the same thing. So you've got one log, and inside, you've got the two old insides being divided. That is not the same as the log of the first thing divided by the log of the second thing. All right, so again, super common mistake. Please try not to be that person. Make sure you pay attention as you solve these problems. Make sure you're comfy with the difference. Questions for me before we wrap up? 2 cubed is 8. So 2 to the third power, in answer to Jacob's question, where did the 8 come from? 2 cubed is 8. Yeah, so this is x squared times 8, which is the same as 8x squared. And then Mark says x to 1/2 cleans up to squared x. What about x to the 4/5? So x to the 4/5, totally unrelated. If we had something like x to the 4/5, you could write this as the 5th root of x to the 4, or the 5th root of x all to the 4. Either of those would be accurate ways to describe x to the, oh shit, no, this, I'm sorry. Yeah, no, 4/5, this is correct, okay, good. Yeah. I don't know if we have time to go through a whole separate problem, Brooke, but I can give you a quick discussion of 23 on homework 19. Let me see. We could always bring this to office hours. So homework 19. Let me see if I can just do something useful on it here. Okay. So this is the same sort of thing as the example we did with the continuous decay rate of 9.5%. Initial population, here's your C. Grows continuously, so you're using C times e to the Rx by 8% per year. So this really is just applying a formula, right? This is straight up just using the formula for continuous exponential growth. Have an earlier problem with that. So remember, if you have continuous growth or decay, they talk about growing at the continuous rate or decaying at the continuous rate. You're using this function, this model. Here they've told you straight up, the initial population is 329. So you'd use this model with C equal to 329. And you're growing continuously by 8% per year. So R is positive 8%. Positive because you're growing, not decaying. And then you just write the 8% as a decimal, 0.08. Alrighty, gangs, I do have to get running. I hope you guys have a lovely rest of your day. If you want to talk to me about anything else, any other problems, anything at all, just come by an office hour, send me a Canvas message. Hope you guys have a wonderful day.